This is Henry Delabèche, one of the founding fathers of geology. His research into mapping and faulting was crucial for establishing key subjects within the A-level and university courses, with his information being utilised to further understand the wider tectonic processes of the UK. And this is the Somerset Basin. Here, on a recent field trip, we walked over a stretch of coastline that Delabèche himself likely investigated almost 200 years ago. Inspired by processes he researched, we aim to explore the effects of differing thicknesses of sediments on fault reactivation and decollements, which is where a fault becomes the main slip plane for the basin.
For both tests, we created a sandbox consisting of alternating layers with a total thickness of 7 centimetres and an initial length of 29 centimetres. In the first test, individual sand layers were 2 to 4 millimetres. To help us understand the stress undergone in both tests, we utilised more circles. The same stress is applied in both tests, but only explained in test 1.
In this initial state, before any compression or extension has occurred, the Moore circles don't reach the failure criterion, and so faults don't occur.
To simulate the opening of the Somerset Basin, we then extended the sandbox by 4 centimetres.
At this stage of the test, it's difficult to see faulting due to thin layers. However, we can see that the Moore circles increase and reach closer to the failure criterion as sigma 3 decreases.
Here we can see that the layers collapse quite quickly and don't retain any structure.
When the Moore circle reaches the failure criterion, faulting occurs.
Sediment was then infilled, simulating a period of deposition where there wasn't any structural movement.
When sand is infilled, there is no extension or compression.
We then compress the sand by 8 centimetres, aiming to mimic the basin closing up.
As compression occurs, sigma 1 increases and the Moore circles grow.
Here we see a number of prominent faults forming, with this fault being the main one.
As sigma 1 increases, growing the Moore circle, it reaches the failure criterion, resulting in faults forming.
On the final push of this section, we can see that the hanging wall doesn't move along other planes, nor form a new fault. Instead, it moves along this newly formed decollement. Here, the newly formed beds are stacked above the previous plane, becoming recumbent. We then compress the sand by 4 centimetres again and extended by another 4, and with no noticeable changes to the layers.
In this test, parameters remained the same except for one crucial difference: the change in thickness. We wanted to test whether thicker layers affected the formation of faults and decollements. As such, we increased the layers to 1 centimetre thick each. On the initial extension, these thicker layers hold their structure far better than the previous test. We can see a fault form in the slope as it collapses. In a real-world setting like in the Somerset Basin, we would expect this to be more pronounced, forming a feature known as a Hofgraben. After infilling, the first fault formed along the surface of the alpha slope from the previous extension. This is due to the fault's tendency to propagate along planes of weakness. After more compression, we saw a long fault form across the box. Unlike the previous experiment, this fault seemed to curve to horizontal as it met the base plate. After another period of extension, we expected fault reactivation and the formation of a decollement. Instead, we compressed the sand again, with a new fault forming.
This experiment yielded some interesting results. We observed frost faulting as the basin compressed, and some normal faulting when the basin extended. As the basin compressed, the number of faults increased and the older structures became distorted. Folding occurred as the faults extended, dragging the beds with them. A similar thing can be seen at Kilve in Somerset. Looking at the graph here, we can see that the alpha angle increases with compression, but when the critical failure occurs and fault forms, the alpha value drops. Based on our hypothesis, it seems that thinner layers displaced more along fault planes and were more likely to form decollements. Thinner layers were more steeply folded, whereas the experiment with thicker layers was more likely to reach critical failure and form new faults. This fault acted the same as the decollement in the first experiment, but after extension and more compression, the fault only reactivated slightly. Instead, a new fault formed at a shallower angle closer to the preferred dip of 30 degrees.
Although the experiments were successful, limiting factors may have influenced the end result. On a repeat of the experiment, we would have used a bigger sandbox. This would have allowed for more extension and compression and helped us investigate the propagation of backthrusting that we believe began to form in Test 2. Other factors like the combined height of the sand layers may have been too high, limiting the amount of faulting.
Thank you for watching. Keep faulting.